Okay, today we want to discuss a very important topic, and that is enthalpy. Okay, so recall from a previous lecture or previous video that we defined energy, or the energy change for a process, delta E, as the ability here to transfer heat, Q, or do work, W. So we'll say for any particular process, delta E is equal to Q plus W. In other words, if we knew how much heat was transferred to our system, or from our system to our surroundings, and we knew how much work was done in either direction, we would have the capacity there to calculate the internal energy change for that particular system. And so what we have to take a look at now a little more closely is what exactly is that work component. And if you recall from physics or from previous discussion, that work is equal to force times distance. And so if you knew how much force you needed to exert over a certain number of, say, meters, that would be able to give you the capacity to calculate work. And so what we're going to talk about in this class mainly is what's called PV work. Okay, and PV work says, okay, the force being exerted here is, let's say you have a cylinder that you want to either expand or contract. And let's say let's say we're going to talk about an expansion. The force opposing that expansion is this external pressure here that's pushing down on this cylinder. And so this accounts for our force component. And if we wanted to account for the distance here, well, think about this. The more that I expand that container, the more work I have to do, right? So the more, if I'm going to expand this, I'll get a blue dotted line here. If I'm going to expand this container to, say, some new volume here, I'm going to have to do more work to expand it to that volume than if I expanded it to a lesser volume here in this red. So the amount of work that you do is proportional to the pressure, but also to the volume change. And so what we'll say for PV work is that W is equal to minus P delta V. And the reason for that minus sign is that when we have volume changes, when we have an expansion, that means our system is doing work. And if we have an expansion, we need delta V here is going to be positive. We need to insert that negative sign ourselves. And so in this way, we'll say that W is equal to minus P delta V. And here what we're assuming is a constant external pressure opposing the force. And we're only talking about PV work, not any kind of mechanical work or any kind of other things that could come into play there. So let's go ahead here and do an example to show you how this works. Here we have 3 liters of gas inside of a flexible container. So again, we'll imagine that scenario where we have say a gas inside of this canister here, and we have a piston there that can move, let's say, and we're going to heat this gas. And so the gas here is going to absorb 690 joules of heat. Okay, so that means positive 690 joules of heat, okay, being transferred into the system. At the same time, though, the system here is going to expand from 3 liters to a new volume of 5 liters. So here we have the piston is going to expand here. And so delta V here is what? Delta V is a positive 2 liters. Okay. And so here we have all the components to calculate the work done if we consider that the external pressure here opposing that is 1 atm. So 1 atmosphere of pressure. Alright. And here we're asked to find actually 3 components. Work, Q, and delta E. And it gives us Q directly, so that one's pretty easy, right? So let's see how this works here. We say that delta E is equal to Q minus P delta V. And so we're going to find the energy change, delta E. Sometimes in other books it's delta U, but we'll just use delta E is fine. And so again, Q was plus 690 joules. Okay, and P is 1.00 atmospheres. And that volume change was plus 2.00 liters. And it might not seem obvious here how we're going to get this to work out, because we have plus 690 joules. And then here we have, if we multiply this together, we have minus 2.00 liters atmospheres. Well, here we need to avail ourselves of this conversion factor here that I'll put over here in this red box, which is that 101.3 joules is equal to 1 liter atmosphere. And so we'll use this conversion factor here, and I'll just include this over here to get this to work out. So 1 liter atmosphere on the bottom, and then 101.3 joules here. So we'll say here that we have 690 joules, positive of course, minus 203 joules once we account for sig figs here, and this is delta E. Alright. And so what we see here is that our system is absorbing heat, 690 joules of heat, but our system is also doing work. Our system is expanding and doing work, and so it's releasing 203 joules of that heat that it's receiving as work. And so the internal energy change here, if we do the math, is only 487 joules. So it's only increasing by 487 joules here. So delta E is 487 joules positive, Q is 690, and the work is minus 203 joules. Let's look at this, I guess, a little more closely here. So recall that we said delta E is equal to Q minus P delta V. And the reason I bring this up is oftentimes we have a system, we want to study it and find delta E. And if we want to find delta E, the most convenient way to do that, unless you want to keep track of this expansion and keep track of the amount of work that's done, is to simply put your system into a place where it can't expand. And if the system can't expand and can't do any work, that's fine, because you have delta V is equal to 0. This whole component here drops out if you have a constant volume scenario. So under situations of a constant volume, delta E can be found by simply monitoring the heat flow. Delta E is equal to Q. And we call this QV, Q sub V. In other words, the heat flow under constant volume scenario. Okay? And these are conditions that we study when we do something like bomb calorimetry, where you have a reaction that's happening inside of a sealed, rigid container that you know is not changing volume, and so you can find delta E directly. Okay, so that's interesting and great and everything, but probably the more true to life scenario is what we call a constant pressure scenario. So again, if we start from the same kind of launching off place here and say that delta E is equal to Q minus P delta V, well, if we can no longer assume that the volume is constant, then this term here no longer drops out. So we have to think about the amount of work that's done. Okay, and so again, what we're going to monitor is the heat flow, Q, and we'll say that Q is equal to delta E plus P delta V. And we'll call this QP, in other words, the heat flow under constant pressure. And although this is a little more difficult because we have to keep track of the work and we can no longer discount it, it is easy to measure. And so usually when we study a reaction in a constant pressure scenario, we're just monitoring QP, and we do this so often that we've given QP a new name, or a special name, and that is delta H, or enthalpy. So enthalpy is nothing more than the heat flow under a constant pressure scenario. And why do I say this is more practical? Well, think of your whole life. You live at a constant pressure scenario just about, right? You have a reaction that occurs in an open flask, or you have an organism that lives at 1 atmosphere pressure. And well, in our next video or two, we're going to do some more examples, both at constant pressure and constant volume scenarios. But for today, we just kind of set out to do a real quick and easy description of enthalpy. And we said that enthalpy was, again, heat transfer which occurs at a constant pressure, and we said that was QP. And so this is delta H. And if we work under constant volume conditions, then we have this real nice result, which is QV is equal to delta E. So again, just kind of two equations for you to keep track of. Okay, and that's all for today. So thanks for watching.